Hello and welcome. Today we're going to be talking about probability. This is just an introduction to probability, so let's take a look and see how some of this will work. Probability assigns a numerical value that represents how likely an event occurs in the long run. And that's really important that it's in the long run. This can be thought of the likeliness of an event. An event E is a subset containing the specific or desired outcomes. So that's like if you want to flip heads, right? Heads is what we're looking for. If you want to roll a 2 on a die or something like that. So that would be the subset. The set containing all possible outcomes, S, is referred to as the sample space. And so in general, probability of event E occurring can be calculated with this formula. The number of outcomes in set E divided by the total number of possible, or the number of outcomes in the sample space. So what you want out of the total possible, if you're looking for the probability of rolling a 3 on a die, on a standard 6-sided die, well, there's 1 3 out of 6 possible sides. Probability can be written as a fraction, a decimal, or a percent, any one of those. For example, probability of E might be 2/8. Well, 2/8, we could even reduce that down more if we wanted to, and we could say that that's 1/4. If we put that into our calculator, that would be 0.25, and if we change that into a percent, that would be 25%. All three of these is perfectly fine. They're all equivalent to each other, that's why we have equal signs in them. An event is a subset of the sample space, meaning that N of E is less than or equal to N of S. Therefore, all probabilities are going to be from 0 to 1, or you could say from 0% to 100%. You can't have more than 100% chance of something happening, and you also can't have less than 0%. So probability is always going to be some number between 0 and 1, or between 0% and 100%. Let's look at a quick few examples. Brian tosses 2 quarters and wants them to land on heads. He wants them to both land on heads. Identify all possible outcomes of tossing 2 quarters, in other words, the sample space, and identify the set of desired outcomes, which is the event. Well, in this case, we could go through and you could do this with a tree diagram, or we can just write the sample space. Most people would have no problem doing this. It's possible that the first coin is heads and the second coin is heads. Or he could get heads and tails, or he could flip the first coin tails and the second one heads, or he could get tails, tails. Now, this right here is our sample space. It's a list of all the possible outcomes. Notice that there are 4 of them. Then, if we're looking for the event in this case says that we want them to both land on heads. Well, it's really just one time that's possible. This right here is the event that we are looking at. So if we were trying to calculate this probability, right, it would be the number of items in our event over the number of items in our sample space. Well, there's only one item in this event, that's heads, heads, and there are 1, 2, 3, 4 possibilities in our sample space. So this probability is 1/4. Or, just like what we spoke about a little bit ago, we could say 1/4, or you could say 0.25, or you could say 25%. If I'm being very honest, I would probably just write it as 1/4 and be done with it, though. In a board game, there's a spinner with numbers 1 through 10 on it. And if you spin and land on a number less than 4, each player pays you $1,000. Ooh, I want to play that game. Identify the sample space for a spin and the set of outcomes that lead to each player paying you $1,000. Well, I have here, kind of like a spinner, I just made a list so that we could easily identify when we win. It says that we win, or each player pays us, if you land on a number less than 4. Notice that it's less than 4, not less than or equal to 4, so not that. In other words, over here, these are the wins, and everything else, this would be where you lose. So these are wins. You can see there's 3 of them. and these ones to the right would be all the times that you lose. And you can see if we count them all, hopefully, there's 1, 2, 3, 4, 5, 6, 7 of them. So there's 7 times we lose and there's 3 times that we win. Identify the sample space for a spin. Well, we have them all, right? We have all 10 possibilities. And then the set of outcomes that leads to each player paying you $1,000. That would be the 1, 2, and 3. So we could say this a couple different ways. We could say the number of elements in E would be 3, and the number of elements in the sample space would be 10, because there's a total of 10 items in the sample space. So the probability of getting E, or in other words, the probability of winning, would be 3 out of 10, or 30%. Now, in classical or theoretical probability, that's based on the ratio of favorable numbers. Classical probability is often called theoretical probability because it's based on theory and not data from some particular experiment. It's what you would expect to happen in a long run. Classical probability tells us what to expect if an experiment were performed a very large number of times, assuming the events in the experiment were consistently likely to occur. So remember that in classical probability, you can't do that in the short run. This is just what happens in the long run. Okay, so a 6-sided die is rolled once. Find the probability of each of these occurring. Well, the probability of rolling a 1, we know that they could get a 1, a 2, a 3, a 4, 5, or 6. So the probability of getting a 1, you can see there's one way to get a 1, and then there's 1, 2, 3, 4, 5, 6. So the number of elements in our sample space is 6, right? That's going to be our bottom number. So the probability of getting a 1 is 1/6. The probability of getting a 4, well, there's only one way to get a 4. So that would be 1, and then the bottom number is going to be 6. The probability of getting an even number, well, let's go through and identify all of the even numbers, right? We have this one, that one, and that one. So there's 3 of them. So there's 3 evens out of the 6 total possible. Next, let's look at not even. Well, if we had these here and the blue ones represent the evens, then all the ones that are not highlighted currently would be the not evens. So 1, 2, 3 of them. There's 3 not even numbers out of 6 total. You'll notice 3/6, you can even leave it like that. There's nothing wrong with that in my opinion. Now, some people want you to reduce these down as much as possible, and we can say that that's 1/2. Okay. And that's it. A class consists of 15 boys and 16 girls. If one student is selected to read the first paragraph of a book, what's the probability of selecting a boy? Well, what we would do is we would look for the number of items in the event that we're looking at, and in this case, it's choosing a boy, right? So the number of boys, and then that's the total number in their sample space. I don't know why I wrote S there. Well, I do because I was thinking ahead. But the total number in their sample space. Well, we have 15 boys and 16 girls. That makes for a total of 31. That means that in our sample space, there would be 31 and 15 of them are boys. So 15 out of 31. This number won't reduce. We're just done. Let's call it good. We'll box it and be done. You could change it into a decimal, but it's not a very nice decimal. So I just leave it. This spinner is spun one time. Find the following probabilities. Well, if we count the total number of possibilities on our spinner, in other words, the number of possible outcomes, we have 1, We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 possibilities in our sample space. That means that's going to be our bottom number for every one of these. So when we have choosing a vowel, it's going to be something over 10 because there's 10 possibilities. Next, let's go through and identify how many are vowels. How many are in the event that we are looking for? Well, we have A, E, and I. Okay, that's easy enough. This would be 3 out of 10. A consonant, that would be the rest of them. So I could go through and count the rest of them and say, well, there's 1, 2, 3, 4, 5, 6, 7. That would work. So it would be 7 consonants out of 10 total. Another way that you could think about that is vowels and consonants, they're opposites of each other. And so if there's a total of 10 and 3 of them are vowels, I could subtract that to get the rest, right? The complement of this. So that's how we could also get 7/10. Next, let's look at getting a capital. Well, if you look at these letters, notice that, let's count how many of them are capitals. This is capital A, capital B, capital C. It looks like every one of these is a capital letter. So there are 10 capital letters, and then remember our bottom number is 10 because there's 10 possibilities in our sample space. This would simplify down to be 1 or 100%. See, it's possible to have a 100% chance of something happening. It's also possible to have a 0% chance of something happening. When you look at our next example, where it asks for the probability of a lowercase 1, we want to count the number that are lowercase, and we'll divide that by the number in our sample space, or in other words, the total possible. The number of lowercase letters are 0. There's 0 lowercase letters here. They're all capital or uppercase letters. So our probability of lowercase is just 0. No need to fancy it up. We don't have to write it as 0 over 10. Let's just say 0. Okay. Next, we have the probability of choosing an A. There's only one A here, so this would be 1 out of 10. And then not A. Again, this is a thing where if we're looking at the complement, I could actually do 1 minus 1/10, and that would be 9/10. Or I could come through and count all of the ones that are not A. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 of these that are not A, so that's why the probability is 9/10. Next, let's look at a deck of cards. If the deck of cards is shuffled well and we choose one card at random, find the probability of choosing a 2. Well, the thing about a deck of cards is you have to actually know what's in it in order to do this problem. So let's go ahead and take a look at a deck of cards. It's not hard. If you didn't grow up playing cards, that's okay. It's very easy to know what's in a deck of cards. So first of all, a deck of cards just has numbers in it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Notice that the 1 is the ace. That's all. It's just a little, that's the only difference that we have here. So when we have diamonds, it starts on a 1 and goes 2, 3, 4, 5, 6, 7, 8, 9, 10. And we also have the hearts that start on 1 and go 2, 3, 4, 5, 6, 7, 8, 9, 10. So just 1 through 10. And then we have our spades starting at 1, 1, 2, 3, 4, 5, 7, 8, 9, 10. So the numbers 1, 2, 3, 4, 5, 7, 8, 9, 10. I know that's a lot. And then after that, we have a jack, a queen, and a king. And it's the same for all the cards. Okay, so these are the face cards. Sometimes they're referred to that. The reason they're referred to that is because notice they have like people on them. So we have J, that's the jack, Q is the queen, K is the king. In each one of these suits is what they're called. So we have suits that are the spades, hearts, diamonds, and clubs. So there's 4 suits, and there's actually 13 cards in each suit. And if you take 13 times 4, because we have spades, hearts, diamonds, and clubs, That's where you get our 52 cards. I also want to point out that there are no jokers. This is a thing that people will often ask me. In a standard deck of 52 cards, there are no jokers. All of the J's are jacks, right? We have 4 jacks, we have 4 queens, we have 4 kings, we have 4 tens, 4 nines, 4 eights, and so on. We have 4 aces. Also, please note that the red cards are hearts and diamonds, and the black cards are clubs and spades. And those are some pretty universal things with a standard deck of 52 cards. If you don't know what's in that, it doesn't take too long to study them and be familiar with them. It'll help you with a lot of math questions. And just playing games. All right, let's go back and look at this now. The probability of a 2. The first thing I want to point out is that it says in a standard deck of 52 cards. So my bottom number is going to be 52. And it's really going to be like that pretty much for all of these. Now, we will simplify them down a little bit, but if we're just drawing one card, then it's what we want out of 52, out of the number of cards in our sample space. When we go to count how many 2s there are, you can see we have 2 of clubs, diamonds, hearts, and spades. There's 4 of them, and so this would just be 4 out of 52. 4 out of 52 is a good answer, but let's go ahead and reduce it down. First of all, I know they're both even, so I could divide the top by 2 and the bottom by 2. That gets me 2/26. And that reduces down because I can divide each of these by 2 again, and I get 1/13. Next, let's look at the probability of a heart. Well, if I count the number of hearts that I have, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Of course there's 13. I just got done telling you that there's 13 of each suit. So there's 13 out of 52. And yes, if you were to put this in your calculator, you'll get 0.25 or 1/4. And that should kind of make sense because we have 1, 2, 3, 4 possibilities, clubs, diamonds, hearts, and spades, and they're all equally represented, so 1 out of 4. Next, let's look at the probability of not red. Well, if I want, I could go through and identify all the ones that are red cards, so that's here and here, and now I can just count how many are not red. And if we take a minute to do that, we get, do all that, you can see we're going to get 26 of them. Right? Half of them are not red. Put that in your calculator, you'll get 0.5 or 1/2. Now, because they have an equal number in each suit, yes, you could actually just go through and say, I know hearts and diamonds are red, spades and clubs aren't. That's 2 out of 4, which is also a half. Next, we have the probability of not 2. Well, if there were 4 that are a 2, then what I can do is just do 52 minus 4 and get 48. So there's 48 cards that are not 2s, or 12/13. I know that one was probably meant to be done after A. I should have gone to B, because those two are complementary to each other, just like C and D. If the nope, sorry, that's heart and red. Probability of a red card, there's 26 reds out of the 52 possible, so that's going to be 1/2. Lastly, the probability of a face card. You can see we've got jacks, queens, and kings, and if you go through and happen to count them all, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This isn't that difficult to do, even if you don't have a picture of cards. This is why it's maybe important to actually know what's in a deck of cards so that you can then do these problems. We get 12 out of 52. We'll work on reducing that down, right? And that'll be 3/13. So if you put that into your calculator, you can change that to a fraction and get 3 out of 13. Next, we're going to look at a different kind of probability. It's called empirical or experimental probability. Empirical probabilities are based on data collected from an experiment. And for small sample sizes, there's no telling what might happen. You might flip a coin 10 times and get tails every single time. Like that's possible. It's not likely, but it's possible. The law of large numbers tells us that if an experiment's repeated enough times, then the empirical probability will approach the classical probability or the theoretical probability. Empirical probability trending towards theoretical is referred to as regression to the mean or approaching expectation. You've probably heard some people say that before, like, oh, they're regressing to the mean. It doesn't necessarily mean that they're doing more poorly. It just means that they're approaching what their true probability really is. A lot of times in sports, we might talk about it when a historically bad team does really well one season and then the next season kind of goes back to being kind of bad. A lot of times they'll use that term there and say, oh, they're regressing to their mean. They're going back to maybe how good they actually are. Now, this is often misinterpreted to mean that the 11th toss of a coin the 11th toss of a coin has to be heads since the first 10 were tails. It's kind of like you think there's these cosmic scales in the universe and that it has to balance out and it has to start balancing it right now. We've had 10 tails in a row, and so of course the next one has to be heads. It's got to balance. That's not true. Okay, what happens really is in the long run, in the next 5,000 tosses, we would expect about half of them to be heads and about half of them to be tails. But you wouldn't be totally shocked if you got, a few more tails than you did heads, right? Maybe we had, it's going to be close, but it's probably not going to be exact. In fact, let's go to, nope. Where did you go? Here we go. So let's look at an example here where somebody is a 50% free throw shooter. And if we just watch them shoot, like, okay, well, they missed. So we can't just say like, oh, they went 0 for 1. They're a 0% shooter. But if we shoot about 10 times, you can see that, well, 7 out of 10. You wouldn't be super surprised if an 80% shooter only made 70%. But if we keep shooting, notice how that line over here on the right-hand side, or those dots, that's the long run average, right? Here we've shot 25 shots, and you can see that they are an 80% shooter. Okay, if we shoot more, they're gonna just kind of keep hovering right around that number. If we go out here to 50, they're really close to 80%. It doesn't mean that they're going to be exactly 80%. It just means that if we take a whole bunch of shots, their long run average is going to be very close to 80%. So those dots, that average is getting closer and closer and closer to 80%. Oh, sorry, this is not a 50%. They are an 80% shooter. I'm not sure why that was there. Let's try and do this with 50 and see if we can get this to load properly. Nope. There we go. Now if we just start shooting a whole bunch of shots, you can see that it's going to be very, very close to the mean. It doesn't mean that it's going to always be exactly 50%. It's just going to say in the long run, it's going to be really close to 50%. That's what experimental probability refers to. A 6-sided die is rolled 20 times, and the results are shown in this table. So you can see that, let's make sure we understand our table. It landed on a 1 5 times. It landed on a 2 4 times. It landed on a 3 4 times. It landed on a 4 3 times. 5 it landed on 3 times, and 6 it landed on 1 time. And if you'll note and add all these together, we get, 9 plus 4 is 13, 16, 19, 20. So there are a total of 20 rolls that we did. Find the probability. Use the results to calculate the following empirical probabilities. Notice that this doesn't say the theoretical probabilities. We know the probability of rolling a 1 theoretically is 1 out of 6, or about 0.166 repeating times, about a 16 to 17%. That's theoretically speaking. But when we actually rolled the die, what happened was we got 5 times it landed on 1, right? So this is the number of items in our that we're looking for over the number in our sample space. And remember, we rolled it 20 times. So this would be 5 out of 20, or 1/4, or 25%. That is definitely different than theoretical probability. Theoretically, it's 1 out of 6. But here with experimental probability, we actually did something. We actually rolled the die 20 times, and this is how it turned out. So the probability of rolling a 1 is 25%. Sorry, our experimental probability of rolling a 1 is 25%. The probability of rolling a 4, we rolled a 4 3 times, and so that would be 3 out of 20. That doesn't reduce down, but if you wanted to write that as a decimal or a percent, it would be 0.15 or 15%. Next, the probability of rolling an even number. So we're going to go through and highlight all of the times we rolled an even. So we rolled a 2 4 times, we rolled a 4 3 times, and we rolled a 6 1 time. That means that if we were to add 4 plus 3 plus 1, we had 8 times that we landed on an even number. So this would be 8 out of 20. Of course, you can divide these down, do some reducing. I know 4 goes into that, so this would be 2/10. Nope, sorry, 2/5. Or a 40% chance of rolling an even number. Now, I know that theoretically it should be a 50% chance, but what we're saying is if you actually do it, this time, the experimental or empirical probability of rolling an even number was 40%. Now, we can either say, well, we just happened to get that, or we could say maybe the dice is flawed. Maybe the die is flawed. I don't know that we've necessarily rolled it enough times in order to be able to make that statement, though. Next, the probability of it landing on a 6. We can see that it only landed on a 6 1 time, right? It landed on a 6 1 time, so this would be 1 out of 20. The probability of a not 6, well, if there's a total of 20 and only one of them's a 6, then all the rest of these are the not 6, which would be 19 out of 20. The probability that it landed on 7, well, notice that it landed on a 1, a 2, a 3, a 4, a 5, and a 6. It doesn't mention 7. So in other words, 0 times. It did not land on 7 ever. 0 out of 20, and we'll just write that as 0. Of course, the probability that it lands on not 7 is the complement. 1 minus 0 is 1. There was a 100% chance that it landed on a not 7. Shaquille O'Neal is a basketball playing legend. He's awesome. Who is famously bad at shooting free throws. Since his career average was right around 50%, he coined the phrase, "Know it to be true, Shaq makes 1 out of 2. That's my Shaq impression. Actually, it'd be a bit more like, "Know it to be true, Shaq makes 1 out of 2. I can't do it. It's embarrassing that this is recorded now forever. I'm sorry, Shaq. In Game 1 of the 2006 NBA Finals, Shaq started the game 1 of 7 from free throw line. Later in the game, he went to the line for 2 more attempts. How many should you expect him to make, and why? Well, maybe the wrong way to think about this is to say, he should make both to get closer to 50%, right? Because he missed a bunch earlier, so now he's got to make a bunch. That's the wrong way to think about this, okay? We can't look at it like that. Instead, what we're going to look at is we're going to say like, hey, he's got 2 attempts coming up, and we know that he's a 50% shooter. He's probably going to make 1 out of 2. In fact, if we look at the sample space of those 2 attempts, we could think of this as all the possibilities for these 2 attempts are that he gets a make and then a make, or he could get a make and then a miss, or he could get a miss and then a make, or he could get a miss and then miss. And so in one of these, okay, in one of them, he ends up making 2. In this one, he ends up making 1. This version, he ends up making 1. And in this version, he ends up making none. And so you can even kind of see it this way. It's like it's most likely that he is going to make 1 out of the 2. That's the most likely event to occur. We can do this only because he's a 50% shooter and a make and a miss are equally likely. Okay, so how should we interpret it? Well, we would expect Shaq to make 1 out of the next 2 shots. Would we be super surprised if he made them both? No, because it's only 2 shots. Would be super surprised if he missed them both? No, because it's only 2 shots. It's a small sample. All right, let's keep going. Next, we're going to talk about the odds. So a lot of times in movies, people, when they come together to do a business negotiation, one person might say like, hey, we're going to do a split and it's 70-30. And then the second person comes back and says like, no way, man, I'm more important. So it'll be like 40-60. And then they end up splitting and they say, okay, all right, 50-50. And in a case like that, when they decide 50-50, what that means is they're saying how many dollars out of every 100 the first person and the second person will keep. In the case of 50-50, it would mean that out of every $100, 50 goes to the first person and 50 goes to the second person. If they went with 70-30, that means that out of every $100, then 70 goes to the first person and $30 goes to the second. So in a case like this, you would want to be the first person. You'd say, hey, I'm more important. I get 70 and you get 30. The odds in favor of an event E occurring is the ratio of the number of favorable outcomes, N of E, to the number of unfavorable outcomes. And I do want to really stress that this is not the total. It's not the total, it's the number of unfavorable, or the number of times you would lose. And that's called the odds in favor. Sometimes we might write this as, actually even what we had before, where we'd say like 50-50. The odds against an event, E, occurring is the ratio of the number of unfavorable outcomes, N of E bar, or E prime, to the number of favorable outcomes, N of E. In which case we would write this as NE bar colon NE. Okay. Some people write it like that. Some people write it like this. My personal preference is the first one. That way we don't confuse the odds with fractions. The ratios can be reduced like fractions, though. Okay, let's go back to looking at a 6-sided die. The odds in favor of rolling a 4. Well, we already know the probability of rolling a 4. I'll just put P of 4 is 1 out of 6. We did that earlier, but that's not what we're looking at now. Odds in favor means we want to put the number of wins, or the number of ways there are to get a 4. That's 1. And we want to compare that to the number of ways that we're going to not get a 4, or the rest of them. And we have all these and these 2. So in total, there's 5 of them, right? 1, 2, 3, 4, 5. So this is 1 to 5, not 1 to 6, right? This is the number of 4s, and this is the number of not 4s. I know that's not exactly proper grammar, but it's the number of not 4s, or the number of all the rest of the numbers. Next, a number greater than 2. If we look back over here, we know that we're going to be able to split this right here. And we can say these are the numbers that are less than 2, or sorry, these are less than or equal to 2. And these are the numbers that are greater than 2. I should have started with that one. So there are 4 numbers greater than 2, and then there are 2 numbers that are not greater than 2, right? These are the wins, or in other words, the numbers greater than 2. And then we also have the rest, right? The numbers not greater than 2. Now, 4 to 2 is fine, but also that will actually reduce, because if you were to think of writing this as a fraction, and you were to write it as 4 out of 2, well, I shouldn't say 4 out of 2, but 4 to 2, that would also reduce down to 2 to 1. And that's actually a little bit more favorable to write it like this. Because it's reduced, it's just a little bit easier to understand. An even number. So if we identify all the numbers that are even, we have 1, 2, 3. So an even number, this would be 3. And then the next number would be the not evens. If we go back and count those, we would say, well, that's 1, 2, 3 of them. So 3 to 3. And in a case like this, yeah, we can reduce that down. 3 to 3, we can divide each of them by 3. And that's going to get us 1 to 1. Some people even call this even odds. I know that's kind of weird, but it just means that you have just as likely chance of getting an even number as you do getting a not an even number. Next, a 3 or a 4. I can see there's 2 of those. So the first number is the 3s or 4s. And in that case, there's 2 of them. And then the next number we have not 3 or 4. And we go through and count all those. We'd say 1, 2, 3, 4 of them. So 2 to 4, which would also reduce down to 1 to 2. We got that just by dividing a 2 out of each of those numbers. 2 is a GCF of both 2 and 4. Next, we have a number less than 6. So here's the 6s. So when we go to do that, the number less than 6, that comes first. There's 1, 2, 3, 4, 5 of those. And then over here, this is not less than 6. And notice there's just 1 of those. So 5 to 1, and that won't reduce at all. We're done at 5 to 1. The last one is a multiple of 3. So let's see, 3 is a multiple of 3 because that's 3 times 1. 6 is a multiple of 3 because that's 3 times 2. Now some people ask, is 1 a multiple of 3? No, it's not. 1 is a factor of 3, but it's not a multiple. Okay, so 3 times 1 is 3, 3 times 2, 3 times 3, 3 times 4, 3 times 5. Those are the multiples of 3. Anyways, we can see that there are 2 of them that are multiple of 3. And then when we count the rest, the ones that are not multiple of 3, we would count those and we'd say there's 1, 2, 3, 4. So 4 of them. I know those can reduce down. 2 to 4 is the same thing as 1 to 2. Let's go back to our deck of cards. One card is selected at random from a standard deck. Find the odds against. Okay, now odds against means that we're going to put like that losing number first. Okay, let's keep that in mind as we go for this. I'm going to bring back up our deck of cards in case not everybody knows these. So if we want the odds of a face card or the odds against a face card, right, we're going to put the not face card first and then the face cards second. And that's because we want the odds against. That means we're going to put that first. When we want against, it's going to be the not and then the in favor, right? Or the lose and then the wins, so to speak. So the odds against a face card. Well, I see that there's, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 face cards. That would go over here for the face cards. And then we want all the rest of them for the not face cards. I could count them all, but there's 52 cards total. 12 of them are face cards, which means 40 of them are not face cards. Next, we could think about reducing this down. So some people even like to write it like that. I know 4 goes into those, so that'd be 10 to 3. Okay, that's probably a better answer for us. 10 to 3 are the odds against a face card. You'll also notice that we do have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 kinds that are not face cards, and 1, 2, 3 kinds that are. So 10 to 3. Next, we've got the odds against a 5, right? Odds against a 5. So when we do this, this is going to be, these are the not 5s here, and these are the 5s. Again, it's probably easier to look at this and say, I can see that there's 1, 2, 3, 4 5s. So I'll put 4 here for the 5s. And then for the rest of them, I would just do 52 minus 4 to get 48. So 48 to 4. And then if you started reducing those down, I know that a 4 goes into each of those. So if I divide both sides by 4, that will get me 12 to 1 odds against. That means that you're 12 times more likely to get not a 5 than you are to get a 5. Hearts, so odds against a heart, that means that we're going to do this by saying we'll put hearts second and we'll put the not hearts first. If you want to count them all, we could say like, oh, there's 13 and 39. That also works. But because there's the same number of cards in each suit, I could even just say that, like, well, as far as the suits go, we have hearts, clubs, diamonds, and spades. I should have changed colors on those. But out of those 4 symbols, 3 of them are not hearts, and 1 of them is a heart. And by the way, if you were to take 13, if you were to take 39 to 13, that would also reduce down to 3 to 1, odds against. Next, a black card. We'll go ahead and put our blanks, and we'll put the black cards in the second because it's odds against. And then we'll put not black. If we go through and count this out, we know that there's 26 not black cards and there's 26 that are black. That will actually reduce down to just 1 to 1, or even odds. Right? You have just as likely chance to get a black card as you do to get not black card. Now, hopefully you've kind of seen how the odds and the probabilities relate to each other, but they are slightly different. Notice that when we do probability, that's the number of items in the sample space, or the total possible outcomes. And when we do our odds, we have the number of elements in E and the number of elements not in E, right? This is the total. So our total goes on bottom, and then the favorable goes on top, what we want when we do probability. All right, let's go ahead and look at just a couple more. The odds in favor of winning a certain scholarship are 1 to 50. Because it's in favor, this is win, and then this is the not win, or the lose. Oops. What's the probability of winning the scholarship? So what we look at is we would say there's 51 total. What's the probability of winning? This would be the number of items in the win, which is 1, over the total, because remember, this is n of e plus n of e prime, or in other words, 1 plus 50. So our probability is 1 out of 51. This is a really, really big mistake that a lot of students make. So students that get the odds and the probabilities correct, first identify that when you're doing the odds, we have a total that's different. That total is what goes down here in the denominator for our probability. The odds are used in horse racing a lot too. I don't really understand horse racing, if I'm being really honest. So it is what it is. But it is really common to talk about the odds when you're doing horse racing. The odds against, okay, so that's the first thing that I'm gonna notice here. The odds against a horse winning is 18 to 1. So what that means is this is the number of times that horse would lose, and this is the number of times that horse would win. Okay, this is our n of e, and this is our n of e prime or e bar. Find the probability that the horse wins and the probability that the horse loses. The probability that the horse wins is going to be the number of wins, so that's 1, over the total possible, 1 plus 18. That's 1 out of 19. The probability that the horse loses, that's going to be the number of times that the horse loses, that's our 18, out of the total possible. So that's 18 out of 19. Notice that those are complementary to each other, right? If I add 1/19 plus 18/19, I get 1. That's every possible outcome. Last one here. The probability of an event occurring is 2 out of 3. Now, notice it doesn't say in favor or against. Whenever it's written like this, you kind of have to interpret it. It says the probability of an event occurring is 2/3. This also means in favor. Like the probability in favor, the probability that this is going to happen is 2 out of 3. Find the probability the event will not occur. Well, if the probability that it does occur is 2/3, then 1 minus 2/3 is the probability that it does not, because remember, those are complementary to each other. Another way to think about it is if I have some basic numbers, 1, 2, and 3, maybe these two are winners, and then this one is not. So the probability of an event occurring might be 2 out of 3, and then so we can see the probability of it not occurring is 1 out of 3. That's just something extra. The odds against the event occurring. Okay. Well, we can think of this. We want n of e prime or n of e bar. Now, because it's odds, it's not that fraction like before. The odds against the event, Well, there's one of those, and then the number of times that the event does occur is 2. So it's 1 to 2 is a way to think about this. We could even think about this as 1/3 to 2/3. And then what we would do to get rid of our fractions is actually multiply both of these times 3. So if I take this one times 3 and the one on the right times 3, I get back to 1 to 2. Okay? And remember, this is against the event. The first number is against, and the second number is in favor. Last one, the odds in favor of the event happening. Well, if the probability of the event is 2/3, right? This means like 2 wins out of 3 total. The odds in favor of the event, you can also think of this as like wins to the number of times you lose. Well, if there's 2 out of every 3 that are wins, then there's 1 that is not a win. There we go. That's it, 2 to 1. So the main takeaway with odds and probabilities, with probability, our denominator is the total possible. Remember back up here. But with odds, when you do the odds, it's just the number of wins and the number of losses, or the number of elements in the sample space. The number of elements favorable to the number of elements not favorable. Keep practicing some of these probabilities and it will come more naturally, but it definitely takes a little bit of practice. Good luck as you continue to work on these probabilities.